Hi everyone. Uh, we're quite glad to introduce our recent research on operator fusion in the field of deep learning compilations. We call it SpaceFusion, and I'm Liang from SGTU. We're going to give our talk in 4 parts here, and I will spend more time on the background and challenge to make alignment to the system audience, and also more time for the abstraction method to highlight our core insights. We will go faster for the other parts, okay? And here's the background section. Our story begins with the hard work for deploying deep learning models as they are getting larger. One of the intermediate results, introduce more DRAM usage and more I/O overheads. Actually, they are taking a great part of the DRAM usage, as we can see here. Fortunately, operator fusion immigrates the problem. It combines multiple adjacent operators into a single one. Fusion is quite good for performance, for it catches the intermediate results closer to the chip cores. For example, shared memories and registers. They are faster than the global memories. And more about Fusion, it brings less DRAM usage, less kernel program launching, and more. That's why Fusion can be cheaper and better, faster. However, Fusion do not always work well, limited by data visibility and memory capacity in their memory spaces. For data visibility, all threads can access the global memory, right? However, with Fusion, for shared memory, only threads in a same thread block can access the same memory space. And for a register, it is even private space for a single thread. If we want to apply fusions, we have to do more about it, right? The first thing is to achieve dependency free between thread blocks for the parallelism because of the limited data visibility. And the other thing is to do for better locality in the thread block for the limited sizes in the memory spaces. With the two things we have to do, Fusion does not really work well for the cases with complex dependencies, which is getting quite common in the current deep learning models. For example, this is an element-wise dependency graph of the multi-head attention. This complex dependency pattern exhibits deeply nested dependencies between elements, layer by layer, and wide dependency ranges covering the whole range of a tensor dimension. It brings super challenge for Fusion. Existing approach for Fusion are in 2 ways. Manually writing Fusion is a better way right now. For they are flexible to design for the complex dependencies, especially for non-element-wise operators. However, they are weak in portability and expensive for high performance. Other way for Fusion is the automatic way. They are promising cheaper and high performance and more portable for different devices and workloads. However, automatic methods are not powerful enough to produce comparable performance in the workloads with complex dependencies. Actually, they are weak in abstraction methods. Most of them uses graph-based state abstraction like data flow graph, DFG, which fails to capture dependencies inside ops. So we need a new abstraction. For the design of the new abstraction, we need to answer 2 questions. The first is, what is the abstraction granularity? Neither too large nor too small. And the second is, what is the abstraction method to capture the dependencies in multiple operators in a whole view? And here's our solution, SpaceFusion, powered by a new abstraction called Space Mapping Graph. The Space Mapping Graph captures both inner operator dependency and intra-operator dependency, and abstract them in a space-wise granularity. It enables SpaceFusion to schedule the data flow easily. SpaceFusion automatically generates efficient fusion via the Space Mapping Graph. And now we're going for the abstraction method. Before we start, we're considering to decouple the dependencies, and here is what we see. In a single operator, for example, the matrix multiplication, given like that, we have two analyses. For each one element of matrix A, it is used n times along the whole range of the loop N, right? And the same for the matrix B in the loop M. We call it one-to-all dependency. And the matrix C in the loop K requires K times of sum. We call it all-to-one dependency. And we have one-to-one inside the operator. For example, the element-wise add, right? And the dependencies in a single operator mostly can be abstracted into one-to-one, one-to-all, and all-to-one dependencies. And also, about the dependencies between operators, we just view it as element-wise equal between them. So the inner operator dependencies can be one-to-one here. And finally, we got the decoupled dependencies inside ops and between ops. And now we come to the space mapping graph. It is quite based on graph method. The vertex is for the computational space. We have two types of space here, data space and iteration space. And the edge is the mapping type between the spaces, namely one-to-one, one-to-all, and all-to-one. And here we go for matrix multiplication. We see that in the visualized version, we have 3 data spaces and 1 iteration space. All the spaces keep dimensional information, and for the themes, are aligned so that they can be in a 3D universal space. And the mappings get 2 one-to-alls and a single all-to-one. Note that the mappings in the SMG are also dimensional here. We see the difference between SMG and the DFG. A DFG has only data space, no dimensional information, and merely for the data flow dependency. However, SMG gives more, but crucial. We can build up SMG for multiple operators via one-to-one mappings, just like we talked about before. And in this case, we get a new fused SMG in a 3D space. Here is a super case of SMG for multi-head attention via building it up. And we can see SMG gives the crucial things in a more organized way, right? This enables us to scheduling SMG easily. Here we introduce the spatial slicer for scheduling the parallelism. We start with the SMG for multi-head attention. The spatial slicers cut against the dim2, which is the only feasible dimension for parallelism, and we got 3 parallel blocks here. And then we introduced the temporal slicer for scheduling SMG block in serial order. We start here. We apply temporal slicing against DIM1, and we got 3 intra-blocks executed one and after. And since they have quite the same computational behavior, so they reuse the limited shared memory space and the register space for better locality. Note that we have 3 all-to-ones in DIM1. They are all reduction computations. So we need to aggregate the intra-block reduction results for a newer one, right? So we introduce aggregations behind the reduction, as the data flow indicates here. However, the reductions in DIM1, namely reduce max, the reduce sum, and the dot in GIM, that we see it as a special type of reduce sum, are chained. They're chained, right? Which means reduce sum uses the results from max, and the dot uses reduce sum and reduce max. So we need to change something in the aggregations so that we can get the correct results. We call it update, then aggregate. Namely, we update the old aggregations before we mix it with a new one. To do that, we conduct a transformation called it broadcast postposition. Our target for this transformation is to find a clearer and shorter passes between the chained reductions so that we can build up minimal update functions. We begin with data flow for the 3 reductions. We tag and name the results here. Let's postposition the broadcast division first. And we got the new flow. The broadcast division goes to the scalar division here, as for the equation given. Next, we postposition the broadcast subtraction. Got it here. It goes to the 2 scalar division here. We add 2 tags here for new important results. Actually, we got the resulted data flow that we really want. Because we can easily recognize the path between the reductions, tagged it as out, sum, and max. And the update function can be get from tracing back the passes here. And finally, they are being inlined in the highlighted spaces. And because of the difference of the functionalities between the 2 slicers, they have different availabilities for the situations in the mapping teams. And we will getting fast from here. And the flow of SpaceFusion is to schedule the SMG build-up using the slicers automatically. SpaceFusion always begins with a larger SMG and schedule it with the awareness of the on-chip memory resource usage against their limited capacities. It tries spatial slicing first for all the dimensions and tries temporal slicing for the dimensions that are not sliced by spatial slicers. And if the SMG is unschedulable for parallelism or overuse of on-chip memories, SpaceFusion partitions the current SMG into a smaller one until it can be scheduled. That's the main flow. Now we go for the evaluations here. We present the end-to-end performance on NVIDIA GPUs with the architecture of Vola, Ampere, and Hopper. We test for the transformer networks. SpaceFusion outperforms in most cases with up to over 8 times of speed up. Note that SpaceFusion is faster than TensorRT, which is powered by many manually trained libraries and templates. Faster than kernel. A kernel is a program powered by flash attention and other sort of fusion implementations. And SpaceFusion can fuse multiple MLP layers up to 20 and LSTM cells, layer norms, and the most important, multi-head attention. SpaceFusion achieves comparable performance to flash attention 2 with up to over 10 times of speed up over PyTorch. And thank you for your interest. Any questions?